This problem deals with the harmonic oscillator or the spring mass system. Uh, so we know that m is equal to 1, ks is equal to 1. So the differential equation, number 1, the differential equation associated to this one is m y double prime plus kd y prime plus ks y equal 0. So we know that m is equal to 1 and ks is equal to 1. Therefore, the equation becomes y double prime plus kd y prime plus y equal 0. So this is a second order differential equation with constant coefficients. So we know that the characteristic equation associated to this differential equation is lambda square plus kd lambda plus 1 equal 0. The roots are, from the quadratic formulas, minus kd plus minus square root kd squared minus 4 equals 2. So now the question is, for what values of kd does the solution go back to the equilibrium point, meaning that the limit of y of t is equal to what? To 0. So the question here is, find kd such that limit of y of t when t goes to plus infinity is equal to 0. Okay, so we know that we have three cases. So case number 1, so we'll go case by case. Case number 1, if we have two real roots, so in this case kd squared, the discriminant, is positive, two real lambdas. Okay, so we have lambda 1 equal minus kd minus square root over 2, and lambda 2 equal minus kd minus plus square root minus 4 over 2. So clearly the damping constant is positive. Remember, the mass is positive. These are physical quantities. The constant of the spring is positive and the damping constant is positive. It may be equal to 0, except the mass, of course, we don't want to have no mass. So clearly the first eigenvalue is negative because we have minus and minus, right? But what about this one here? Is it the lambda 2? Is it negative or positive? So clearly we have, since kd squared minus 4 is less than kd squared, then the square root, remember, 4 is less than square root of kd squared, and since kd is a positive quantity, so this is equal to kd. So if you take now minus kd, in other words, I'm taking kd to the other side, it becomes, the quantity becomes negative. So lambda 2 is also positive, negative. So both of them are negative, and we know in this case that the general solution is given by y equal c1 e lambda 1 t plus c2 e lambda 2 t. Since both of them are negative, lambda 1 and lambda 2, then limit of y of t when t goes to plus infinity is equal to 0. Okay, so now in this case we are fine. The solution will always go to the equilibrium, to the equilibrium position. Okay, so at rest position. So now what value, for what values on KD we have KD squared minus 4 greater than 0. So remark. So KD squared minus 4 is positive if and only if KD squared greater than 4, and again if we take the square root we get KD, again why? Because it's positive, so that's why I can put KD here, greater than square root of 4, which is 2, not plus minus 2, okay? So as long as KD is greater than 2, we have the limit of y of t when t goes to plus infinity is equal to 0. Excellent. Now what happens if KD is equal to 2 or less than 2? So that's of course if KD is equal to 2 or KD squared is equal to 4, then we have the discriminant here equal to 0. So in this case we have a double root, and that's case number 2. Case number 2, case where KD squared minus 4 is equal to 0, or KD is equal to 2. So in this case, there is only, we have double lambda equals to minus KD over 2 or minus 1. So we know that the general solution in this case, the general solution is y equal C1 e minus t plus C2 t e minus t. Okay? And again, in this case, we have limit of y of t when t goes to plus infinity is equal to 0. Pay attention that this one goes to 0, no problem. But for this one, you have to use your knowledge of calculus 2, where because the t goes to plus infinity and e minus t goes to 0, so you have infinity times 0, you may have to use opposite rule to show that indeed it goes to 0 as well. So it goes to 0. And now we have the third case, case 3, where KD squared minus 4 is less than 2, or KD is less or than 2. I'm sorry, less than 0. So it's negative discriminant. So in this case, we have complex eigenvalues. So we have lambda equal minus KD plus minus I square root of the opposite of the discriminant, which is 4 minus KD squared over 2. So remember, the inside, the discriminant here, this one, is positive because we took the opposite of the one that we had before. The one we had before was negative, there is a minus, and that's why we have the I. So we need to find the real part and the imaginary part of the eigenvalues lambda. So this is minus KD over 2 plus minus I square root 4 minus KD squared over 2. So the real part is the number minus KD over 2, and that's, so we have what? So now we know that the general solution is, so if I call that one lambda equals alpha plus minus I beta, okay? So alpha is the real part of lambda and beta is the imaginary part. Then we know that the general solution is y equal C1 e alpha t cosine beta t plus C2 e alpha t sine beta t. Okay, I can factor out e alpha t, and then we get e alpha t times C1 cosine beta t plus C2 sine beta t. So clearly, what's going to control the long-term behavior of y is alpha. Okay, so if alpha equal minus KD over 2 is not equal to 0. So in this case, KD is not equal to 0, yes? And since KD is positive, so alpha is negative. And because alpha is negative, then y of t will go to 0 as t goes to plus infinity. So we are fine. But if alpha is equal to 0, okay, then y is equal to c1 cosine beta t plus c2 sine beta t. And in this case, y is periodic with period pi 2 pi over beta. So you see, in this case, there is no way we are going to go what? To 0. It keeps going up and down, up and down. So the conclusion is, as long as we have damping, see, as long as KD not equal to 0, then, so we must have damping, then limit of y of t will eventually go to 0 as t goes to infinity.